Under its turbulent clouds, Venus is a planet of unforgiving heat, oppressive pressure, and volcanic deserts hundreds of kilometers long, a world remolded by world-shattering eruptions and extraterrestrial geology. With the exception of some eerie, grainy surface pictures, Venus preserved its mysteries for centuries. No one had ever really glimpsed what lay behind the mask, until Magellan. On the 4th of May, 1989, Space Shuttle Atlantis had launched its third flight from Kennedy Space Center, carrying on board a very special payload, the very first deep space probe to be launched by a space shuttle, a Venus probe about to make history. For 4 years, the Magellan spacecraft boldly explored our closest neighbor, mapping 98% of its surface to a resolution of 100 millimeters or better. The pictures it returned broke our illusions of Venus forever, and that is what I'm going to share with you today. Join me today as we delve into the breathtaking photos of Venus NASA's Magellan mission returned, the surprises they uncovered about Venus's tumultuous past, and the mysteries still that continue to this day. Mariner 10 took some of the earliest photographs of Venus in 1974, observing Venus's thick cloud cover during a flyby on its route to Mercury. A year after that, the Soviet Venera program planted a spacecraft on the planet, which transmitted the first, and to date only, photos from the surface of Venus. They are a barren, otherworldly scene, but the pictures recorded data from only minuscule fragments of the planet's surface. The cameras on the landers could only capture a few meters in any direction and were destroyed in a matter of hours by Venus's stifling pressures. The Pioneer Venus orbiter, also called Pioneer Venus 1 or Pioneer 12, gave some radar mapping data in the 1970s, but its resolution was poor and its images partial. Picture mapping the planet, but Google Maps wouldn't allow you to zoom in closer than 75 kilometers. New York City would be a single pixel, so really difficult to create a good map. Also, Pioneer 12 didn't cover the top and bottommost regions of Venus. That's equivalent to a map of Earth with all of the Arctic and Antarctic circles absent. NASA concluded they could do better. They wanted to observe it all: landforms, tectonics, impact and chemical processes, erosion, and even learn about Venus's interior. So they embarked on a grand mission to capture the whole surface of the planet in ultra-high detail, together with a gravitational map that would offer a glimpse into what is going on underneath. That job was Magellan. Now, before I display Magellan's images, you must appreciate 3 important engineering breakthroughs that enabled Magellan's mission to be so revolutionary. Firstly, to pierce the thick atmosphere of Venus, Magellan enhanced Pioneer's rudimentary radar altimetry. Engineers employed a 3.7-meter high-gain Voyager antenna and parts from previous missions to form a synthetic aperture radar, SAR, that took several readings of every region from different positions in orbit. These combined readings mimicked observations from an extremely large antenna, yielding unprecedented surface details. Second, Magellan took a polar orbital route mapping Venus in north-south strips, with each of its 3-hour, 15-minute orbits. Altogether, it made 6 243-day mapping cycles. Cycles 1 to 3 surveyed the planet's surface, and cycles 4 to 6 took gravity field data. By the end of its first cycle on May 15, 1991, Magellan surpassed its 70% mapping target, covering 83.7%. At the completion of Cycle 3, it had mapped 98% of Venus at 250-meter resolution. The probe ended up transmitting back more data than all of NASA's entire history of planetary missions combined, 150 gigabytes in total. By today's standards, it admittedly isn't that great. Your phone likely contains more storage space. But for the early 90s, it was impressive. Finally, after its third mapping cycle during September 1992, Magellan sent a continuous radio signal to the NASA's Deep Space Network. Depending on how the probe's acceleration varied as it circled the planet, this would cause a variation to the radio signal through the Doppler effect, enabling scientists to decipher Venus's gravity field. This revealed information about the planet's interior structure and density distribution. The images I'm about to show you are 10 times sharper than any previous radar images taken from Earth or orbiting spacecraft at the time, and 250 times sharper than Pioneer 12's data. For the first time, we actually got to witness what was hiding beneath those dense, poisonous clouds. Let's have a look. Where earlier missions had shown only vague silhouettes, Magellan uncovered a world in stunning detail, unveiling for the very first time the surface features of our next-door neighbor. This mosaic took 10 years to assemble, with most of the radar data from Magellan's data. Let's zoom in a little more and take a quick tour. When you get close to Venus, you right away notice there are no craters. In comparison to the Moon or Mars, it's relatively untouched, with Magellan only able to detect 940 impact craters on the entire planet. Most small impact craters are not there because their meteors burn up in Venus's atmosphere. And the rest of the craters we did locate weren't what was expected. Consider these 3 craters as an example: How, Danilova, and Aglaonite. When it impacts, surface debris is thrown out and creates the pale yellow blanket-like structures surrounding each crater. Crater ejecta leave behind a characteristic mark and shape that assists scientists in deciding the angle and energy of impact and how long ago it happened, the composition of surface and subsurface materials, and much more. What's interesting about these crater ejecta is they all show sinuous flows in a flower-shaped pattern, not unlike lava flows. They're made of molten rock and remain this way for way longer than expected because of Venus's extremely high surface temperatures. The Adivar crater is another excellent example of Venus's distinctive ejecta patterns. On airless bodies such as the Moon, ejecta material from the impact travels in an arced ballistic trajectory, but on Venus, the ejected debris interacts with the dense atmosphere, producing strong winds that scour the material outward in low-lying streams. This produces strange streaks such as the horseshoe-shaped one we observe here that occur only on Venus. Lastly, the 90-kilometer-wide Adams crater boasts a 600-kilometer outflow tail, probably composed of impact melt or magma, which may persist in its liquid state for much longer because of the high temperature and pressure on Venus. The paucity of these craters indicates Venus's surface is really young. In fact, gravity, data gathered by Magellan, confirms the theory that Venus experienced a global resurfacing event about 300 to 500 million years ago. So what might have triggered such an event? 10 volcanoes. Many volcanoes. We already knew Venus had volcanic formations prior to Magellan, but we never imagined that a whopping 85% of the planet is blanketed with volcanic flows, such as these pancake domes, 65 kilometers across, with wide, flat tops under 1 kilometer high. They probably formed from highly viscous lava, which cooled and pulled back later, resulting to the pits and cracks you can observe in the image. Or these large lava flows extending by hundreds of kilometers across the broken plains under 2 giant shield volcanoes, Sapas Monsan Matmons. By comparing the different shapes and patterns of the volcanic plains, scientists are able to distinguish between various volcanic formation processes, ranging from localized shield volcano eruptions to gigantic regional lava flood events. Talking of Matmons, let's get closer to the look. Standing at a dizzying height of 8,000 km tall, it's nearly as big as empty Everest. It's also a shield volcano, distinguished by its wide, gently sloping flanks. They're normally created by fluid lava flows, and such as the Mauna Loa in Hawaii. If you find Matmons as cool as I do, and you'd like to have some of Venus's fire in your Pochetto add some excitement to your day, then you might want to look at the wallpapers we have designed over on Patreon for your phone, desktop, or tablet. We've also got some really stylish posters over on Display to Venus and the other planets too. Check them out with this QR code or find the links in the description below. Now back to the volcanoes. Shield volcanoes are not the only kind of volcano you'll see on Venus. Small volcanic domes like these are also very common features on the planet's surface. Unlike shield volcanoes, volcanic domes are formed by small bulbous masses of lava too thick to flow very far. As it slowly exits the vent, the lava piles up and cools on the sides. This cluster of volcanoes sits between rough lava flows in the east and smooth lava flows in the west, indicating 2 different types of lava overlapping, although the specifics of the process are still not known. The prevalence of volcanic and lava flows on Venus validated that volcanism had a strong influence on the formation of Venus's surface and led to the hypothesis that the planet could be volcanically active to this very day. In 2024, researchers who were re-examining Magellan's archival database discovered that 2 volcanoes actually erupted while the probe looked on in the early 1990s. This corroborated a historic finding in the year before that Matmons had also erupted in 1991. So what's happening down below? What is Venus's mantle like? A clue to those answers lies in the surface coronae, such as this 500-kilometer-wide Yavin corona. When heated, upwelling magma from the depths of a planet's mantle reaches the surface, or the lithosphere it leaves its signature. On Earth, our tectonic plates move over this magma hotspot, building volcanic chains such as Hawaii or flood basalts. But Venus has only one single tectonic plate, so mantle plume activity pushes the surface upwards before collapsing as the magma solidifies. The outcome? These coronae, even though they are hundreds of millions of years old, many coronae are still in good shape. There are around 500 of them, spread out over the entire planet in a pattern that doesn't match plate boundaries, and their features indicate a lithosphere that's too thick or rigid to fracture into mobile plates such as Earth's. All of this evidence indicates a peculiar style of lithospheric deformation in which the crust remains largely fixed but is pushed, pulled, and deformed by forces beneath. This stagnant lid planet model may also be involved in Venus's runaway greenhouse effect. On Earth, our tectonic plates perform essential processes, such as burying oceanic carbon. When Itrane's atmospheric carbon interacts with mountain rocks to create new minerals, which slowly make their way to the oceans and eventually find themselves stored in seabed sediment. This sediment is then subducted when an oceanic plate sinks the seabed back into Earth's magma layer, a process that regulates Earth's temperatures and the concentration of carbon dioxide in our atmosphere. Since Venus's crust is stagnant and devoid of tectonic activity, this regulatory process can't take place. Instead, heat builds up beneath the surface, and greenhouse gases are not effectively removed from the atmosphere. The hotter the interior becomes, the more unstable the system, until the entire lithosphere is turned over in a worldwide resurfacing process, and the cycle repeats. We don't know precisely when the previous resurfacing event on Venus took place, but NASA's technical report after Magellan indicates that it did about 300 million years ago. Another intriguing sign of Venus's singular tectonics and mantle process are the tesserae, which we can observe in the highland areas of the planet. They are unique geological structures with very deformed ground, having a tile-like feature. They cover approximately 8% of the surface of Venus and are largely rural in location. As being rural, some of the oldest seen surface features on Venus, they formed approximately 750 million years ago. The USSR's Venera 15 and 16 missions initially identified these formations in the 80s, but Magellan fleshed them out in glorious detail, such as in this picture of Alpha Regio, one of the most dominant tesserae on Venus. Scientists still aren't certain exactly how tesserae develop, but the two top hypotheses suggest they are probably composed of volcanic rocks, or they form part of Venus's continental crust, deformed by compression or expansion. If that's the case, they'd be portals into Venus's geological past, and maybe even reveal to us what the climate was like billions of years ago. Intriguingly, Magellan actually did catch the first signs of active tectonics being seen on another planet in the solar system, on Venus's Aphrodite Terra, a continental region about the size of Africa. The left-hand image was captured in late November 1990 during Magellan's initial flyby of Venus. The right-hand image was captured 8 months later, as the spacecraft passed over the area for the second time. Notice the bright, stream-like patch that materialized? That's probably the product of a landslide, which was potentially caused by a Venus quake. On October 13, 1994, after finishing one of the most highly successful deep space missions in history, the probe made its final descent into the atmosphere of the planet it had studied so devoutly over the last 4 years. As it plunged toward the surface, it continued to transmit data about Venus's upper atmosphere until it was consumed by the intense heat and pressure. More than 30 years on, Magellan remains our only source of information about Venus, and in keeping with any good mission, it raised more questions than answers. Did Venus ever have water? If so, would the planet have been able to support life? How has the planet changed over time? Is Venus still volcanically active today? Alongside NASA's future Veritas and Da Vinci missions, they will seek to determine all of them and so many others. Launching in 2028-2030, they will transform our knowledge of Venus again. Da Vinci Plus will examine Venus's clouds through 2 gravity-assist flybys, as well as send a descent probe deep into the Venusto, get a better understanding of its gases, chemistry, and water history. Even though it isn't expected to survive the landing, the probe will collect valuable data and images on its hour-long descent to the planet's scorched surface. Meanwhile, the Veritas spacecraft will be a Venus orbiter, just like Maven already, orbiting Mars. During the 3 Earth years it will be orbiting our neighbor. Its mission will be to look for signs of current volcanism and tectonic activity by measuring heat emanating from the surface and studying the composition of Venus's tesserae. All this information will inform us on just how different Venus and Earth are. Could our neighbor actually be a window into our own future, or is it more similar to our hot, bad twin? Until next time, thanks for watching.